Hello everyone and welcome back, and today we're going to be talking about the Chinese Remainder Theorem. This theorem is over 1700 years old, originating in ancient China, and yet it still shows up in today's cryptography, computer science, and even calendar calculations. So we're going to start with, what does the Chinese Remainder Theorem solve? Imagine someone tells you when you divide a number by 3, so n divided by 3, the remainder is equal to 2. And when you divide the same number, n, by 5, the remainder is equal to 1. Is there a number that satisfies both conditions? There's two ways that you could do this. The first way is by guess and check, or you could use the Chinese Remainder Theorem, which would guarantee that a solution exists, and that the solution is unique modulo the product of the moduli. In this case, it would be 3 times 5, which is 15. So the Chinese Remainder Theorem is about solving systems of congruencies, like x is equal to a1 mod m1, and x is equal to a2 mod m2. And as long as the moduli m1 and m2 are pairwise coprime. So now we're going to go over the official statement. So if we have x is congruent to a1 mod m1, and x is also congruent to a2 modulo m2, and the moduli being m1 and m2, but in general cases going up to mk, are pairwise relatively prime, then there exists a unique solution modulo where m, capitalized, is equal to lowercase m1, m2, all the way up to mk. In other words, there's exactly one solution between 0 and capital M minus 1. So now let's actually solve some examples. So we're going to start off with a simple system, being x is congruent to 2 mod 3 and x is congruent to 1 mod 5. So we're going to do this a cheat way just to get the idea of what we're doing. So all the numbers that are 2 modulo 3 are going to be 2, 5, 8, 11, 14, 17, and keep going. And then the way that we would do the guess and check method would be just by checking which one is 1 mod 5. So as we could see, 11 would be 1, because 11 mod 5 is congruent to 1, as multiples of 5 are 5 and 10, and 11 is just one number above 10. Meaning that for this example, x would be equal to 11. And since the moduli are 3 and 5, the solution is unique modulo 15. So the full solution would be x is congruent to 11 modulo 15. And then we can write it a different way as well, because any number of the form 11 plus 15k will satisfy both congruencies. So this will be known as the CRT in its simplest form. So now we have a full example where we're going to use the entire Chinese remainder theorem method. So we have x is congruent to 1 modulo 4, x is congruent to 3 modulo 7, and x is congruent to 2 modulo 9. So we're able to use the CRT because 4, 7, and 9 are all pairwise coprime, which means that the GCD of 4 and 7 is equal to 1, the GCD of 4 and 9 is equal to 1, 7 and 9 is equal to 1, and again 7 and 4 is equal to 1. So what we need to do is compute the product, which is taking our capital M, which is equal to 4 multiplied by 7 multiplied by 9, which here will give us 252. So now we need to compute each partial modulus. So here what we need to do is we need to split up our M into 3 different parts because we have 3 different numbers. So our first one, M1, is going to be M divided by 4, which gives us 63. Our second one is going to be M divided by 7, which gives us 36. And finally, we get M3, which is going to be equal to M over 9, which is equal to 28. Now, what we need to do is find each inverse. So we'll do a little dotted line down the middle and start writing on the right side. So we need numbers y1, y2, and y3 such that 63 multiplied by y1 is congruent to 1 modulo 4. And then we need 36 y2 is congruent to 1 modulo 7. And finally 28 y3 is congruent to 1 modulo 9. So we're going to solve them each one by one. So the first one we're going to do, we'll do in orange. We're going to have 63, and we're going to have this equal to 3 modulo 4. So because this can simplify from 63 all the way down to 3, what we're able to do is replace our 63 in our original equation, which is 3y1 being congruent to 1 modulo 4, which makes things a lot easier to work with, because now we can just try values where 3y1 would be congruent to 1. So we're going to try 3 multiplied by 3, which will give us 9. And as you can see, 9 is congruent to 1 modulo 4, which means that our y1 is going to be equal to 3. Next up, we're going to do our finding of y2. So again, we're going to just try to find what 36 is equal to in mod 7. And easy enough, this time 36 is actually congruent to 1 mod 7, meaning that when we have our 1 multiplied by y2, it has to be congruent to 1 modulo 7, which means that our y2 is congruent to 1. And then finally, we're going to have our 28y3. So we're going to try to see what 28 is modulo 9. And again, this one is quite simple because 28 modulo 9 is congruent to 1. So putting back into our original equation, we get y3 is congruent to 1 modulo 9, meaning that y3 is also equal to 1. Now what we will do is we're going to build our formula to get our final answer. So we have x, which is our original question, is equal to a1 capital M1, Y1 plus A2, M2, Y2 plus A3, M3, and Y3. So now we're able to just answer this by having our A1 being equal to our 1. Then we're going to have our M1, which is our 63, and our Y1, which is equal to 3. Now we're going to add this with our A2, which is going to be the 3 from the original all the way over here. So we're going to have 3, and then our M2, which is going to be equal to 36, and then finally our 1. And then finally we're going to add our 2 from our original, which is our A, and then we're going to multiply that with M3, which is our 28, and our Y3, which is equal to 1. Now adding this all together gives us an answer of 353. But we're not done just yet, because as you remember from the original, we still have this value of m, our total m, which is the 252. And as you can see, this 353 is larger than it. So what we're going to do is we're going to reduce by taking this modulo 252, which is kind of just like a subtraction, which is 353 minus 252, which for this one would give us 101, which will be our final answer. So we can write that x is congruent to 101 modulo 252. And this is the unique solution between 0 and 251. Thank you for watching, and I'll see you in the next one.